In this session we will discuss about preparation of amines, chemical properties of amines and diazonium salt. The first method for preparation of amines is by reduction of nitro compounds. Nitro compounds are reduced to amines by passing hydrogen gas in the presence of finely divided nickel, palladium or platinum catalyst. The reduction can also be carried out with the help of metals in acidic medium. Nitroalkanes can also be similarly reduced to corresponding alkanamines. The reduction using iron scrap and hydrochloric acid is also preferred. Reduction means removal of oxygen and addition of hydrogen. The main reducing agents are hydrogen or palladium in presence of ethanol, tin and HCl, iron and HCl, and also lithium aluminium hydride. Here is a memory tip to remember the reduction of nitro compounds to amines. The logic is very simple. The nitro group, that is NO2, will be converted to amine group, that is NH2. For example, in the first case, nitromethane is converted to methylamine. Similarly, in the second case, nitroethane is converted to ethanamine. Similarly, nitrobenzene is converted to benzanamine or aniline. The second preparation of amines is by ammonolysis of alkyl halides. The process of cleavage of CX bond by ammonia molecule is called ammonolysis. This reaction is carried out in a sealed tube at 373 Kelvin. The primary amine thus obtained behave as a nucleophile and can further react with alkyl halide to form secondary and tertiary amines, and finally quaternary ammonium salt. The simplified version of ammonolysis is given here. The process of cleavage, that means bond breaking, of a carbon halogen bond in an alkyl halide by ammonia is called ammonolysis. Alkyl halide means a halogen attached to an alkyl group. Example is CH3Cl, where chlorine is the halogen and CH3 is the alkyl part. An example is given here. CH3Cl combines with ammonia to form CH3NH2 and HCl. The mechanism is also given here. The halogen, that is chlorine of the alkyl halide, combines with hydrogen of the ammonia molecule and forms HCl. The remaining NH2 parts attach with the methyl group and forms methanamine. Thus, according to definition, the carbon halogen, that is carbon chlorine bond, is broken by ammonia molecule, and this process is called ammonolysis. Two questions are given here based on ammonolysis. Write the chemical equations for the following reactions. Reaction of ethanolic ammonia with chloroethane. Second one, ammonolysis of benzyl chloride and the reaction of the amines are formed with 2 moles of CH3Cl. In the first question, C2H5Cl, that is the alkyl halide, combines with ammonia molecule. Similar in the case of ammonolysis, one of the hydrogen from ammonia molecule combines with chlorine of the alkyl halide and forms HCl. At the same time, the remaining NH2 part of the ammonia molecule combines with C2H5 and forms C2H5NH2, that is ethanamine. This process continues until all the hydrogens of the amine are replaced by C2H5. Finally, the product formed is N-diethyl ethanamine. In the second question, benzyl chloride, that is C6H5 CH2Cl, combines with ammonia molecule. The same process takes place here, and finally it results in the formation of N-dimethyl phenyl methanamine. C6H5 signifies the benzene ring, that is also called phenyl. The third method for preparation of amines is by reduction of nitriles. Nitriles on reduction with lithium aluminium hydride, that is LiAlH4, or catalytic hydrogenation, produces primary amines. This reaction is used for ascent of amine series, that is for preparation of amines containing one carbon atom more than the starting amine. Nitriles are compounds having the general formula RC triple bond N, where R can be any aryl or alkyl groups. If lithium aluminium hydride, that is LiAlH4, or hydrogen in the presence of nickel is given above the arrow mark, this signifies reduction, that is hydrogenation. The memory tip for reduction of nitriles to amines is given here. The cyanate part, that is C triple bond N, is converted to CH2NH2. That is, reduction take place. 2 hydrogens each is added to both carbon and nitrogen. Thus, C triple bond N is converted to CH2NH2. For example, CH3C triple bond N will be converted to CH3CH2NH2 in the presence of lithium aluminium hydride. Similarly, CH3CH2 C triple bond and will be converted to CH3CH2CH2NH2. The fourth method for preparation of amines is by reduction of amides. The amides on reduction with lithium aluminum hydride yield amines. The general formula is given by Rc double bond O NH2 in the presence of lithium aluminum hydride is converted to RCH2NH2. The memory tip for reduction of amides to amines is given here. The carbonyl group, that is C double bond O, is converted to CH2. Or in other words, the C double bond O is reduced to CH2. That is, oxygen is removed and hydrogen is added. Two examples are given here. CH3C double bond O NH2 is converted to CH3CH2NH2. Similarly, a C double bond O NH2 attached to a benzene ring, that is C6H5, C double bond O NH2 is reduced to C6H5CH2NH2. The next method for preparation of amines is Gabriel phthalamide synthesis. This synthesis is used for the preparation of primary amines. The phthalamide on treatment with ethanolic potassium hydroxide forms potassium salt of the phthalamide, which on heating with alkyl halide followed by alkaline hydrolysis produces corresponding primary amine. Aromatic primary amines cannot be prepared by this method. The Gabriel phthalamide synthesis can be simplified when it is explained in three steps. In the first step, the hydrogen of the phthalamide combines with OH of the potassium hydroxide and forms water molecule, which gets eliminated, resulting in the formation of potassium salt of the phthalamide. In the second step, the potassium salt of the phthalamide combines with CH3Cl. In this step, the potassium combines with chlorine of CH3Cl and forms KCl, which gets eliminated, resulting in the formation of a compound in which the potassium is replaced by CH3. The compounds so formed further react with NaOH to form the primary amine. The third step can be further simplified here. Even though this is not the actual mechanism, the concept can be easily understood. The phthalamide part combines with two molecules of NaOH. NaOH can be written as HONa. The two hydrogens each from NaOH combines with the CH3N and forms the primary amine CH3NH2. The remaining part ONA attaches with the phthalamide part and forms the resulting molecule. The sixth method for preparation of amines is Hoffman bromamide degradation reaction. Hoffman developed a method for preparation of primary amines by treating the amide with bromine in aqueous or ethanolic solution of sodium hydroxide. In this degradation reaction, migration of an alkyl or aryl group takes place from the carbonyl carbon of the amide to the nitrogen atom. The amine so formed contains one carbon less than that present in the amide. The general formula for Hoffman bromide degradation reaction is given here. The memory tip for Hoffman bromide degradation reaction is given here. The logic is very simple. The carbonyl or C double bond group is removed from the amide. An example is given here. CH3C double bond NH2 plus Br2 plus 4 NaOH gives CH3NH2 plus Na2CO3 plus 2NaBr plus H2O. Next we will discuss about the chemical reactions of amines. Acylation. Aliphatic and aromatic primary and secondary amines react with acid chlorides by nucleophilic substitution reaction. This is known as acylation. In simple words, the addition of the acyl group, that is C double bond Cl, in general C double bond X, to the amine is called acylation of amines. A simple example is given here. CH3NH2, that is methyl amine, react with the acid chloride CH3C double bond Cl. In this reaction, the chlorine of the acid chloride combines with one of the hydrogen of the methyl amine and forms HCl, which is eliminated, resulting in the formation of the following amide. Two other examples are given here. Try to understand the concept based on the same logic. Similarly, amines react with benzoyl chloride, that is C6H5COCl. This reaction is known as benzoylation. An example is given here. Methanamine combines with benzoyl chloride to form N-methyl benzanamide. A simple example for benzoylation is given here. In this reaction, methanamine combines with benzoyl chloride to form the corresponding benzanamide and HCl. In this reaction, the hydrogen of the methanamine combines with chlorine of the benzoyl chloride to form HCl. The remaining CH3NH of the methanamine combines with the C double bond C6H5 of the benzyl group and forms the corresponding amide. The next is carbylamine reaction. Aliphatic and aromatic primary amines on heating with chloroform and ethanolic potassium hydroxide forms isocyanates or carbalamines, which are foul-smelling substances. Secondary and tertiary amines do not show this reaction. This reaction is known as carbalamine reaction or isocyanate test and is used as a test for primary amines. The memory tip for learning carbalamine reaction is very simple. The NH2 part is converted to the NC, that is cyanide. A simple example is given here, and we can see that the NH2 part is converted to NC and the carbalamine formed is a foul smelling substance, and we can easily understand that the amine was a primary amine. The secondary and tertiary amines do not show this reaction. The next is reaction with nitrous acid. Primary aliphatic amines react with nitrous acid to form the corresponding alcohols. Aromatic amines react with nitrous acid to form disonium salt, which we will study in the later part of this video. The memory tip for learning reaction of amines with nitrous acid is given here. The logic is very simple. The NH2 part changes to alcohol or OH. That is, RNH2 changes to ROH. Two examples are given here. Methanamine react with nitrous acid to form methanol. Similarly, ethanamine react with nitrous acid to form ethanol. Two examples are given here where ethylamine react with nitrous acid to form ethanol. In case of aromatic amines like aniline, it is converted to benzene disonium chloride, that is disonium salt, which we will study in the later part of the video. The next is reaction with aryl sulfonyl chloride. Benzyl sulfonyl chloride C6H5SO2Cl, which is also known as Hinsberg reagent, react with primary and secondary amines to form sulfonamides. The Hinsberg reagent does not react with tertiary amines, so Hinsberg reagent can be used to distinguish between primary, secondary and tertiary amines. In this reaction, the hydrogen of ethanamine combines with chlorine of Hinsberg reagent, that is benzene sulfonyl chloride, to form HCl. The remaining part of ethanamine combines with the Hinsberg reagent radical to form N-ethyl benzene sulfonamide. The secondary amine will also undergo this reaction since there is a hydrogen present in the secondary amine. But in the case of tertiary amine, all the hydrogens are replaced by alkyl groups. So tertiary amine does not undergo the Hinsberg test. Next we will discuss about electrophilic substitution reactions. The first one is bromination. Bromination means addition of bromine. Aniline react with bromine water at room temperature to give a white precipitate of 2,4,6-tribromoaniline. To understand the concept of bromination, we will discuss the bromination at the ortho position. In this case, one of the bromine combines with one of the hydrogen at the ortho position and forms HBr, and the remaining bromine attaches the position of the hydrogen at the ortho position. The same process happens at the para and meta positions. Next we will discuss about nitration of aniline. Nitration is carried out with the help of nitric acid and sulfuric acid at 288 Kelvin. The products formed are para-nitrotoluene, meta-nitrotoluene and ortho-nitrotoluene. Due to less steric hindrance, the para-nitrotoluene is the major product and accounts almost 51%. If the position of NH2 and NO2 are almost close to each other, this causes repulsion and this is called steric hindrance. In the para-nitrotoluene, the NH2 group and NO2 group are at the two extreme positions, so there is less chance for steric hindrance, so the para-nitrotoluene is the major product. In case of meta-nitrotoluene, the positions of NH2 and NO2 are a little more close together, so there is a chance for little steric hindrance, so its percentage is 47%. In the case of ortho-nitrotoluene, the NH2 group and NO2 group are very close to each other, so there is more chance for steric hindrance, thus the percentage composition is only 2%. Here is a memory tip to remember the nitration process. HNO3 can be written splitted as OH and NO2. OH plus NO2 gives HNO3. The hydrogen at the ortho position of aniline combines with OH of HNO3 and forms H2O. The NO2 group then attaches at the position of the same hydrogen, thus resulting in the formation of ortho-nitroaniline. In the similar manner, the NO2 group is attached at the meta and para positions. Next we will discuss about sulfonation. In this process, with the help of sulfuric acid, a SO3H group is attached to the para position of aniline. It is called sulfanilic acid, which then undergoes rearrangement to form a Switter ion. In the sulfonation process, H2SO4 can be written as the combination of OH and SO3H. A hydrogen from aniline now combines with the OH of H2SO4 and form water molecule. The remaining SO3H gets attached to the position of the same hydrogen,
resulting in sulfonation. Mainly the hydrogen at the para position undergoes this type of cleavage and thus form sulfonolic acid.